Hello, everyone. I'm re-recording this. I think I literally lost my recording. I'll have to see, but I'm just going to make a more concise version of what we did today. And yeah. Okay, first thing I want to talk about a little bit about is kinetics and what's going on with these elementary steps. So here I have an example on the left, and we can kind of break down different possibilities and different concepts. So the first thing we need to know, though, is that slow steps, they're the only thing that can affect the reaction, okay? And also known as the rate determining step. But we can sometimes incorporate these fast equilibriums, and that can kind of change how we look at which steps are involved. But first I want to define what an intermediate is and what a catalyst is. So an intermediate is something that gets produced, but then consumed. So a good example of this would be C here. The reactant C was produced, but right away it was consumed in step 2, okay? A catalyst is something that is a reactant. It gets consumed, but then somewhere along the way it gets released and then produced, so it can catalyze other reactions. So a good example of that would be A. So we see it being consumed in the beginning, but we didn't ultimately take it because we produced it right back at the very last step. Okay. And what about fast equilibrium? Okay. So let's say that step 2 was our slow step. We found this out experimentally. So step 2 is our slow step. Okay. And we also know that step 1 is fast equilibrium. Notice these double arrows here. Okay, very important. So these will be fast. Every step that's not fast or that's not slow is fast. So this bottom reaction, though, it doesn't have double arrows. It's not in equilibrium there. So I'm just going to completely ignore this, okay, for now. Well, for the entirety of this example. So for a situation here, we know our slow step and we have a fast equilibrium right on top of it, okay? If our fast equilibrium was after our slow step, that wouldn't really help. That wouldn't do anything for us. It wouldn't affect the rate law, nothing like that, okay? So here, when we have a fast step, we can directly connect it to the slow step, okay? We can cross out these intermediates here, okay? And what we're left with is kind of like, we have a flow of reactions happening, and therefore we can consider A, B, and this other B to be involved in our rate law. Okay, so the rate law for this would look like this. Okay, if our fast equilibrium was the last step, that wouldn't help us here if the slow step is before it. Okay. If the top reaction was not in fast equilibrium, okay, and the second step was just the slow step, all we can say is that the rate equals C plus B there. Okay. We cannot connect the first reaction with the second reaction, even though it seems like there's this intermediate relation there. If it's not in equilibrium, we cannot consider it for the rates, okay? Next thing I want to talk a little bit about is stereocenters, how to identify them, what they are. So stereocenters are points where there are 4 distinct groups, okay? Those distinct groups can be anything. But if you have a carbon that is attached to 2 methyls, that's not a stereocenter. If you have a carbon that's attached to 2 hydrogens or 3 hydrogens, that's not a stereocenter. It needs 4 distinct groups, okay? This also means no double bonds in the atom you're looking at for stereochemistry, because when you have a double bonded carbon, that reduces the number of bonds overall it can have, or substituents it can connect to, reducing it to 3, or if you have multiple double bonds or a triple bond, 2. So again, we need that 4 distinct groups, no less, no more for carbons. So in this case here, we see that the carbon highlighted is not a stereocenter because it has 2 methyls connected to it. It has 2 methyls, 1 hydrogen, and then this rest of the molecule portion. Okay, so the first carbon here is not a stereocenter. What about these? Well, they're connected to 3 hydrogens, and so that can't work either. It needs to be 4 distinct things. What about here? At this position, it can be a stereocenter because we have a chlorine here. I didn't write it, but there's also a hydrogen there. So that's another, that is another component. Then there's an isopropyl group. And here we have an this is a sec-butyl group. Those are 4 distinct components of that is connected to this carbon here. And at carbon number 4 there, let's see. So here we have connected to a methyl group, an ethyl group, and this entire rest of the molecule, as well as a hydrogen, which is assumed. Those are 4 things. So there's also a stereocenter there as well. Okay, at carbon number 5, there's 2 hydrogens coming off of there, so that can't work. And at carbon number 6, we have 3 hydrogens coming off of that carbon. Okay, we're going to jump to Newman projections a little bit. So for Newman projections, basically what's happening is you're looking at this molecule, at the carbon, kind of head on. So this is my pencil here, and it's as if I were to look at this pencil directly like that, okay? I wouldn't be able to see this long bond here. I would just be able to see the carbon in front of me, which is what this dot here, this center represents. The back carbon is represented by the open circle, okay? So I will keep my front carbon in red and my back carbon in green here. Okay, so here we're going to draw out what this molecule looks like, okay? By the way, for high energy molecules, for high energy Newman projections, we're going to want to depict it as eclipsed. So that means everything is overlapping each other, as well as having the largest groups overlapping each other, which creates a lot of instability. The molecule really doesn't like that. It's a lot of tension, and it doesn't enjoy it. A lot of steric clashes. So that's why it's high energy. A low energy, relaxed Newman projection would be staggered, and it would have as much space in between the large groups as possible, using like hydrogens as kind of buffers between large groups. So here I'm going to start out with my red carbon. Always draw out what your molecule looks like. For example, if you're going to name it, I highly recommend, or find out how many stereocenters are in a Newman projection. I always recommend drawing it out. It is way too difficult even for me to tell what it looks like just from the Newman projection without drawing it out. So I have my red dot there, and then I have my green carbon. I'm going to represent the bonds between them by this white bond. I can't see that when in the Newman projection, but it's there. So on this red carbon, I have a methyl group coming out. I have an isobutyl, so that will just look like this. And then I also have an ethyl group. Okay, On the green carbon, I have a bromine, I have a methyl, and a hydrogen. Okay. Now, personally, I can barely tell what's going on in this really ugly molecule, and I try to make it look a lot better, to interpret, to name, and to figure out what stereocenters there are. It's a little bit better. So I'll show you where my original red carbon was and my original green carbon here. So I'm going to find the longest chain with the lowest numbering scheme. So here, 1, 2, 4, 1, 3, 4. The numbering scheme is pretty much the same if you go either way, but let's see. Yes, I believe it'll be shorter if you go this way, the smaller numbers that way. Okay, so we know we have a we'll start here. 1, 2, 3, 4, 5, 6. We have a bromo at 2. And at 3, we have a methyl, and at 5, we have a methyl. So 3, 5 dimethyl. For alphabetizing, only the M counts here, not the D. At 3, we also have an ethyl. Okay, so putting this all, and this is also a hexane. Putting this all together, we'll have 2 bromo, 3 ethyl, 3, 5 dimethyl, hexane. Okay. Now jumping a little bit to RS configurations. I know this is really tricky, but it doesn't have to be. So here are just some ground rules, some ground information about labeling RNS. Here, the first point I wanted to make is how is priority even assigned in the first place, right? So it's by atomic number. So here's the kind of the priority. So sulfur, you're going to see sometimes that has a higher atomic number than oxygen, which is higher than nitrogen, which is higher than carbon, which is higher than hydrogen. Carbon, which is higher than hydrogen. And what are you really doing when labeling RNS? When you are assigning priorities, it's really like a race. It's a race to the highest priority or the highest atomic number. And I should probably fix it. Highest atomic number. And I'll show you what I mean. Okay, and here we're going to deal with these other situations in a second, because those are some situations you'll run into. I also want to emphasize that labeling priorities is not like a summative game, okay? When I started out learning this, I was under the misconception that, oh, like the sum of this section is greater than, like the weight is greater than this area, so the heavier one should have, the one with more stuff should have higher priority. That's not the case. So if we see here, this chain of carbons has a lot of carbons in it. It has a lot of weight, more than this section here. But it's not about that. It's about which direction can you reach the highest atomic number first, okay? And in the shortest number of branching events, okay? That's why it's a race. What do I mean by branching events? Branching events, just, how many times you keep going and branch out. Okay. So here, just starting out, we see a stereocenter here. And because this carbon is going to be, connected to other things. Oops. Okay, so this carbon is connected to, a bunch of things here. And one thing I didn't draw, which is usually not going to be drawn, is the hydrogen, okay? And so I know for sure that my hydrogen is wedged, okay? It's wedged, which means it's coming toward me, okay? Because the oxygen here is dashed, okay? It's going into the page. Um, Whenever there is something dashed, there must also be something wedged with it. And so that's how I know that there is a wedged hydrogen there. Otherwise, how would I know? So you can assume that this hydrogen is coming toward us, okay? Typically, all the time actually, we want our lowest priority group, which is usually hydrogen, but it doesn't have to be. It doesn't have to be hydrogen. Sometimes a methyl group will just be the lowest priority group there, and that's fine. We want it to be in the back though, okay? So that's where it belongs. We want it in the back. So that's not the case here. So what do? I'll tell you. But first, I just want to solve this problem like normal, and figure out, label my priorities, figure out, which direction is it going in, and then I will deal with this later, this hydrogen later. Okay, that's the last part. So already I see that here I have a carbon here and a carbon here, and I have an oxygen there. Okay, so that oxygen is higher priority than any of the carbons or hydrogens, so that's going to be automatically number 1. Okay, we know that the hydrogen is number 4. And now we're stuck here. Okay, we have 2 carbons here, so we're stuck. We need to branch out again to see what's next. So here, if I branch out again, okay, if I branch out again, on the bottom area, I'm stuck with another carbon. Okay, there's also hydrogens about all around, but that's not really important. They don't really help. So on the top, however, on the top this way, we run into a nitrogen right away. And we know that nitrogen has a higher atomic number than carbon, okay? And so therefore, this upward direction, this top carbon here, wins priority over the bottom one. Despite the bottom one having so many more carbons and so many things, it's not about a summative game here. It's about a race to which branch can reach the highest atomic number first. Okay. Okay. So then we're going to put this all together. We're going to connect 1, 2, and 3. Okay. 1, 2, and 3. And this is going counterclockwise. Okay. So this is me S. Okay. So right is clockwise. Okay. It's going in like the right direction, like this way. S is counter clockwise. It's going this way. Okay. Right could be interpreted as, R could be interpreted as right-handed maybe. S is like left. It's short for sinister, so that's like indicating left. So counterclockwise. In this case, we have an S. However, remember when I told you that hydrogen is not in the right place, okay? So a simple thing, only one small task needs to be done to fix this, okay? That is just to turn this S into an R, okay? And R becomes your final answer, okay? That is only when the lowest priority group is not in the place that it belongs, which is the back. So all you need to do when you have a hydrogen or a low priority group, doesn't have to be hydrogen, that's not in the back, your R will turn into an S as your final answer, or an S will turn into an R, and that's what you'll take as your final answer. Okay, simple as that. You just do a flip, you just do a switch. Okay. All right. So we figured that out. Another situation is where we have double bonds. So what do double bonds mean when labeling R and S, basically you count the atom twice, okay? So let's say you have a situation like this, okay? So here, we can label our number 1 and number 4 pretty easily, right? So our hydrogen will be number 4. Our oxygen right there will be number 1. And then we have to decide between this way or this way to be, which priority. So they both start out with carbons there, okay? So nothing we can do with that. We need to branch further. But we do branch further, and then, oh, we're stuck again. We have oxygens both ways in the same amount of branching events here. We get oxygens in 2 branches. We get oxygens. What do we do? So like I said, the double bonds will count as 2 times, okay? You can really consider this like when you're kind of like at the end of your rope here, because sometimes you'll have situations where you have double bonded carbons and stuff like that, and that's not as useful because it's just a bunch of carbons when there's usually higher priority groups in the picture. So again, like these are really like at the end of your rope, or when there's no other higher priority groups in the molecule at all. Okay, so because the double bond is counted as twice, like 2 times an atom, it's like that this carbon here is bonded to 2 oxygens, and so this one will win priority. This will be number 2, and this will be number 3. So we're going to connect 1, 2, and 3. 1, 2, and 3. This is going clockwise. And is our lowest priority group in the back? Yes. Okay, we don't need to touch it. So this is R. Perfect. Final answer. Okay, so that was just an overview on the most important topics for this quiz, but please feel free to email me on anything at all. And there's also the practice quiz as well. All right.